Good morning, everyone. Today we will present our project about the comparison between HTTP and HTTPS communication in computer network using Wireshark. In this project, we capture network traffic to analyze how a computer communicates with a website through different protocols. But before we start our presentation, let us introduce ourselves first. My name is Riti Angguni. You can call me Nina.
My name is Putu Nadin Saskirani Putri. You can call me Nadin.
My name is Febby Anggariani. You can call me Febby.
My name is Kadek Denis Krisna Febrian. You can call me Denis.
Next. So in this experiment, we use Wireshark to capture network traffic while browsing a website. The capture was performed during browsing, and the analysis focused on several protocols such as DNS, TCP, HTTP, and HTTPS. For testing, we access neverssl.com for the HTTP website and ssouniksa.ac.id for the HTTPS website. Next. First, we look at the DNS query process. When a user types a website name in the browser, the computer needs to know the IP address of that specific website. So the client sends a DNS query to the DNS server. We can see from the capture, the DNS query packet is sent from the client 192.168.1.5 to the DNS server 192.168.1.1. In the DNS query show assets.msn.com because the modern website load additional resource from external domains. The domains ssouniksa.ac.id and neverssl may not appear because their DNS resolution was already cached. Next is the after receiving the query, the DNS servers process the request. Then the DNS server send a DNS response back to the client. The DNS server send a DNS response back to the client 192.168.1.5. The response you can see in the packet details contain the IP address of the requested domain, which will be used by the client to establish communication with the destination server. Next is the TCP three-way handshake. After the DNS process resolves the domain name, the client establishes a connection with the server using the TCP protocol. TCP ensures reliable communication between the client and the server, but before any data is transmitted, TCP performs a three-way handshake process to establish connection. Next, the TCP three-way handshake, including SYN packet, is the first step. The client sends a SYN packet to the server to start the connection, and then this packet indicates that the client wants to initiate a TCP connection, and it also contains the initial sequence number used to start communication. Next. The step 2 is SYN ACK packet. It's after receiving the SYN packet, the server responds with SYN ACK packet. This packet acknowledges the client's request. It means the server is ready to establish the connection. The packet includes both the SYN flag and the ACK flag. Next. Finally, the client sends an ACK packet to confirm the server is response. This packet completes the TCP three-way handshake. After this step, the connection between the client and the server is successfully established. Next is the HTTP communication. After the TCP connection is successfully established, the client begins sending data requests to the server using the HTTP protocol. HTTP is an application layer protocol used for communication between web browser and web servers. In this analysis, the client accessed the website neverssl.com using the HTTP/1.1 protocol. Next. In this stage, the HTTP GET request, the client sends an HTTP GET request to retrieve a website page from the server. The GET method is used to request resource such as HTML page or other web content. In this capture, we can see the client requesting neverssl.com using HTTP/1.1. Next. After receiving the request, the server processes it and sends a response back to the client, which is HTTP response. The server responds with the status code 200 OK, which means the request was successful. The response contains the HTML content of the web page, which will be displayed in the browser. Next. Next is the HTTPS communication. HTTPS is a secure version of HTTP that uses TLS encryption. This encryption protects the data exchange between the client and the server. And in this analysis, the client accesses the website ssonixa.ac.id, which use HTTPS with TLS version 1.3 for secure communication. Next. To start secure communication, the client sends a client hello message. This message initiates the TLS handshake process. It contains the supported TLS version and shipper suite. It also includes the server name indication, which specify the domain being accessed. Next. After receiving the client hello, the server responds with a server hello message. In this step, the server selects the TLS version and the shipper suite. These parameters will be used to establish a secure connection. Next. After the TLS handshake complete, the client and server begin exchanging encrypted data. In Wireshark, these packets appear as TLS application data. Because the data is encrypted, the actual content cannot be directly read. Next.
Next, I'm gonna explain about encapsulation and decapsulation process. So, in computer networks, data is transmitted through a process called encapsulation and decapsulation as it passes through the layers of the OSI model. So, encapsulation process is a process that data moves from the application layer to the physical layer, and each layer adds its own header information to the data before transmission. While the decapsulation process is the reverse process that occurs to the receiver side, where each layer removes its header information until the original data reaches the application layer. So you guys can see the process of encapsulation on the PowerPoint started from application layer where data is created, for example, like HTTP requests, and then next to the transport layer where it adds TCP or UDP header for forms a segment, and network layer for adds IP address, data link layer adds MAC header and trailer, and the last is physical layer where data is converted into a bytes and transmitted through the network media. Next. Now I'm gonna explain the analysis of OSI layer using a Wireshark. As you guys can see in the screen, there's two different of capture. The first capture is HTTP process, where basically the layer 7 is application layer, which is responsible for communication between application, such as web browser and the server. So we take the HTTP and HTTPS process on the Wireshark. From the Wireshark capture, we can see the HTTP GET request sent from 192.168.1.5, which is the client device, to the destination IP address on the screen that already appeared. And the next one is HTTPS communication. We can see several packages related to the TLS handshake process. The first package is the client hello, sent from the device or the IP address that sending the data to the destination IP address or the server who receiving the TLS handshake request. Next. So next is layer 6 or the presentation layer. Presentation layer is responsible for data formatting, translation, and encryption, where on the layer 6, we just only can capture on the HTTPS process because HTTPS process using encryption, and on HTTP, we don't have capture on that because there's no encryption on the process. So in HTTPS communication in this layer using TLS or SSL to encrypt the data before it sends to the transport layer. In client hello is used to start the TLS handshake, and it informs the server about the client security capabilities, such as supported TLS version, random values for the case generation, supported cipher seeds, session ID, until additional extensions such as server name indication. And next, the server respond with a server hello, which is confirm the encryption parameters that will be used. And after the handshake process is completed, the server sends change shipper spec that indicating the following communication will be encrypted. And for the layer 5 or the session layer is the layer manage communication session between the device. Its function to establish, maintain, and terminate communication session between the client and the server. And we don't have any capture on Wireshark because it's considered an abstract layer on the OSI model. So the function of session layer are usually integrated into other protocols such as TCP or TLS handshake. Next is transport layer or TCP. So basically in TCP, it's including on layer 4, which is the transport layer. It's responsible for reliable data transmission between the devices. And the main protocol that we using in here is TCP, which is ensure the reliable communication by using sequence number, acknowledge number, window size for flow control. For example, the client sends data with the sequence number 1301 and the server responds with acknowledge number 498, indicating that the data has been successfully received. The window size determines how much data can be received before another acknowledgement is required, and this process continues until the communication session is completed. Now, on the layer 3. Next. So in the third layer or network layer analysis is a layer using the IP or internet protocol to manage logical addressing and routing. For example, like search IP, search IP and destination IP. So the first capture is the HTTP get, and the second capture is HTTP 200. Okay, so the first is client sends HTTP request to the server using IPv4 and TCP as the transport layer. And you can see a lot of information such as packet header length, total packet length, first package, and checksum. And after that, the HTTP 2000 will respond and go to the next layer. Okay, next. Now it's HTTPS. So the HTTPS using the client hello and the server hello. So it starts from search IP. During the TLS handshake, the client hello package is sent by the client to initiate a secure connection with the server. It contains information such as supported shipper seeds and the server name indication or SNI. We're using sso.undixa.ac.id, and then the server respond with a server hello, which confirms the shipper set and version of the LS to be used for encrypted session. Following this, application data is encrypted and security transmitted over the connection and stabilize the TLS handshake. Next, for the second layer. The second layer, or data link layer, is a layer which handles communication within the local network using a MAC address. So, the first capture is the HTTP GET, and the second capture is HTTP to 100% OK. So, the client sends an HTTP request to the server using IPv4 and TCP as the transport layer, and then the internet frame has a length of 5051 bytes with the source MAC address to the destination of MAC address. And after processing the request, the server sends a HTTP 200% OK response back to the client. The response frame also has a length of 551 bytes with the source MAC address and the destination MAC address on the screen. Then the Ethernet type is again IPv4. Next. For the HTTPS on the layer 2 or data link layer, the first capture is client hello capture and the second is server hello. So Ethernet at layer 2 identifies devices using MAC address that are unique to each device on the local network. In client hello package, the source MAC address belongs to the client and the destination MAC address belongs to the server. While in the server hello package, the source of MAC belongs to the server and the destination MAC belongs to the client. Both packages are transmitted as a Ethernet frames containing data and an Ethernet header. Ethernet ensures that the frames are delivered between devices in the local network and identifies the package as IPv4, which is then forwarded to the layer 3 or the IP for addressing and routing to the other network. And the last is the physical layer analysis. Next. So, layer 1 or physical layer is the lowest layer on OSI models and server as the physical, meaning for transmitting data bits over a network. This layer responsible for sending electrical, optical, or radio signal representing data from one device to the other. On the Wireshark, we can't find or we can't capture the OSI layer directly because the tool capture package after they are processed by the networks or interface card at data link layer, which is the layer 2. Therefore, the physical layer is explained conceptually referring to a physical transmission media used by a network such as Wi-Fi or Ethernet cables, which is transmit data in the form of electrical signal, radio waves, or light signals. That's all about my explanation, and the next material will be explained by my friends. Thank you.
Next, what are the OSI layer and TCP/IP layer? OSI layer is a 7-layer conceptual framework by International Standard Organization or ISO that standardizes how devices from different vendors can communicate in a network. And TCP/IP, on the other hand, is a set of communication protocol used to connect devices in a computer network or over the internet, ensuring that data can be sent or received securely. While OSI serves as a theoretical reference model, TCP/IP grew out of real-world implementation needs, making it more practical and widely used on the internet. Next, we will talk about OSI and TCP/IP model comparison. From number of layers aspect, OSI has 7 layers with very strict and strictly functional boundaries. And TCP/IP model only has 4 layers. For standard aspect, OSI model is formally published by ISO or IEC standards. Meanwhile, TCP/IP model is governed by International Engineering Task Force, or IETF. Next. For transport layer, in OSI, transport layer is responsible for end-to-end communication, error detection, flow control, and segmentation of data into packets. In TCP/IP, the transport layer does the same thing, and it's implemented that famously through UDP and TCP. When you expand a TCP packet, you will see the TCP flags such as SYN and AC key, and it's clearly visible in the capture. It's confirming that TCP/IP implements transport layer communication concretely. Next. For pilot reliability and encryption aspect. For encrypted HTTP traffic, the pilot is readable. When you click on HTTP packets, you will see the full GET request and headers, and the URL is being accessed. It's all plain text, but it for HTTP traffic or HTTP over TLS is completely different. TLS encrypt the application layer pilot before it leaves the sender. So in Wireshark, you will only see a block label application data. And for OSI model, the pilot reliability depends on the layer. And for TCP/IP model, pilot reliability depends on encryption. Next. Next, here is the visualization of OSI and TCP model. In OSI model, the application, presentation, and session are separately to clearly define their functions, such as formatting layers, handling applications, data formatting, and session management. However, in TCP/IP model, these three layers are combined into the application layer, because in real network systems, their functions are usually handled directly by the application, so separating them is not necessary. The transport layer exists in both models, and it's responsible for end-to-end communication and data delivery, such as using TCP and UDP. The network layer in OSI corresponds to internet layer in TCP/IP, which handles IP, addressing, and routing packets between networks. And for data links and physical layers in OSI are combined into the network interface layer in TCP/IP, which handles hardware communication and data transmission over the physical network. Next. So here is an example detailed packet that uses the HTTP protocol. For each row in the packet's detail panels represent one layer in the TCP/IP models. Example, frame 19084 as network access layer. The protocol shows 551 bytes on wire and 551 bytes capture. For Ethernet 2 is represented as network access layers 2. The protocol shows source MAC and it handles physical addressing on local network. Next, Internet Protocol version 4 or for IPv4 as internet layer. This protocol shows source and destination of addressing and routing. TCP or transmission control protocol as transport layer. This protocol shows source port and destination port with sequence and AC key. This ensures end-to-end delivery. And the last is HTTP or Hypertext Transfer Protocol as application layer. This protocols provides web communication between client and server. Next.
Okay, next I'm gonna present an analysis of HTTP and HTTPS communication using packet capture from Wireshark. In this presentation, I will explain the difference between HTTP and HTTPS, the TLS handshake process, how certificates are used for authentication, and difference in payload transmission between both protocols. But before we jump in, let me explain to you the difference between HTTP and HTTPS. So basically, HTTP and HTTPS are protocols used for communication between client and server on the internet. The main difference between them is the security. HTTP sends data without encryption, while HTTPS secures the communication using TLS or SSL encryption. Because of this encryption, HTTPS is much safer and is widely used for websites that handle sensitive information, such as login credentials or payment data. Next. So now, we have right here is port 18 versus port 443. So, in network communication, HTTP use port 18, while HTTPS use port 443. HTTP send data in plain text, which means the data can be intercepted and read by anyone monitoring the network. In contrast, HTTPS use TLS encryption on port 443 to protect the transmitted data and ensure secure communication between the client and the server. Next. On this slide, we can see an example of HTTP communication captured using Wireshark. So I'm using filter HTTP right here to show the HTTP communication used on port 80. Because HTTP does not use encryption, the data inside the packets can be clearly viewed in Wireshark. This means that anyone monitoring the network could potentially read the transmitted information. Next, in this screenshot, we can see HTTPS communication captured using Wireshark. Instead of HTTP, the protocol displayed here are TLS, as you can see right here, which indicates encrypted communication. Even though the packets are captured, the actual content cannot be read because the data is encrypted using TLS. Next. Okay, after we compare port 18 versus port 443, we jump in right into TLS handshake. So, when a client connects to a website using HTTPS, the TLS handshake process occurs before any data is transmitted. This process allows the client and the server to establish a secure connection. This process allows the client and the server to consist of several steps, including client hello, server hello, certificate, and the finish, which indicates that the secure session has been successfully established. Next, so we move on. The first is client hello. In this screenshot, we can see the client hello package captured in Wireshark. I'm using the filter right here, TLS handshake type equal ones. So the TLS client hello package was sent from client 192.168.1.5 to the server 103.176.173.198. So we can see right here the packet details. This package indicates the start of the TLS handshake process, where the client offers several zipper suite that can be used for communication encryption. As you can see right here in the screenshot, the client offers many zipper suite. Okay, next. So after receiving the client hello message, the server responds with a server hello package. So as you can see right here, I'm typing the filter TLS handshake type 2 equal 2. So this show the server hello message. So in this package, the server select the zipper suite. As you can see right here, the zipper suite is TLS 128 GCM SHA 256. So the zipper suite to be used for the encryption communication between the client and the server. Next. So after that, we move on to the certificate. In this slide, we can see the certificate sent by the server during the TLS handshake. This certificate is used to authenticate the server and prove that the website is being accessed is legitimate. The certificate is issued by a trusted certification authority, which ensures that the server identity can be verified. Next. Okay, so we move to certificate information. As you can see right here, this display the certificate that are in the server right there. So this include the issuer. So the issuer was Microsoft Corporation. Validity, so it's valid in 2026 February until 2026 August. So it's basically like maybe 6 months or maybe 6 months. This validity period ensures that the certificate can only be used within a specific time frame to maintain security. So after this expired, you have to buy a new certificate for maintaining the security. And finally, certificate also include public key and also a secret key for you. That public key is used in the encryption process during secure communication. Okay, next. Okay, next we move into the payload, HTTP and HTTPS. So in networking, payload refers to the actual data contained with a package. This data represent the information being transmitted between the client and the server. In web communication, the payload may contain elements such as HTML code, CSS styling, JavaScript files, or other web page content. Next. So as you can see right here, this is a HTTP payload. For example, we can see the HTTP GET request as well as the HTML structure of the web page, including elements such as HTML, head, text, and the other element. This means that anyone intercepting the network traffic could potentially read the transmitted data. And if you log in into some website with HTTP, you can see the username, the password, so it's basically just dangerous for you. Okay, next. Okay, this is HTTPS payload. Unlike HTTP, HTTPS encrypt the payload using TLS. In Wireshark, the payload appears as encrypted application data. Because of the encryption, we cannot see actual content such as HTML or CSS. As you can see right here, I'm opening the TLS screen, but nothing appears on this. So the data can only be deciphered by the client and the server that possess the correct encryption key. Okay, next. Okay, and this is it for our presentation. Thanks for tuning in. Thank you.